Okay, so hello and welcome everyone. This is the live session number 8 for week 8 for the course Introduction to Semiconductor Devices. As you know, the instructor for this course is Professor N.K. Emani from IIT Hyderabad, and I am Samadhan Kamble, your PMRF TA for conducting these live sessions. I am a PhD scholar at IIT Madras, working in the experimental high energy physics in the CMS experiment at Large Hadron Collider. So I think this is enough about me, and let's get started with our live session number 8. As you know, the session progresses as follows. In the first 10 to 15 minutes, I'll briefly cover the recap of this week's content, giving a refresher which will be helpful in the problem solving. Then we'll move to the assignment problems, very similar to your current set of assignments, and of course to your end sem examination that you will give at the end of the course. Okay, so let's start with a quick recap of the week 8's lecture content. Let me go to the slide number 1. So in the previous week, that is the week before this Monday, we talked about the MOS capacitor, its importance in the MOS devices and so on. We specifically mentioned the MOS capacitor's electrostatics when we applied different potential at the gate, how the different regimes arises like accumulation, depletion, inversion in the MOS capacitors. So in this week, we primarily focused on the CV characteristics of the MOS capacitors. These are extremely important when characterizing the MOS capacitor, and of course in the MOS devices such as MOSFETs that we will be encountering in the next weeks and so on. Okay, so if you just uh, look at the diagram here, I have shown the CV characteristics. So you can clearly see here that it is a p-type substrate I am considering. So the substrate is p-type substrate, which means the MOS capacitor is NMOS. So for the NMOS, as we have already studied in quite a bit detail, that when Vg is negative, the accumulation of the majority carriers occurs at the oxide interface, and the capacitance is purely the oxide capacitance, and we can see that the balancing charge, if you consider the balancing charge on the other side of the plate, it appears on the interface of the uh, gate and the oxide layer. So we can the oxide and the semiconductor layer. So in this region, this is the accumulation region, and Cox is basically the epsilon of the oxide and the thickness of the oxide layer, and you can see that this is purely geometric. So oxide and the thickness is fixed in any MOS capacitor. So this is the fixed geometric capacitance. But when we go into the region where we apply Vg more than 0, we will see that the depletion region starts as the majority carriers are depleted or pushed away from the junction, and we can see the capacitance decreasing, and which is actually given by C depletion as epsilon of the silicon, the semiconductor, and the width. So you can see that the balancing charge in the depletion case appears at the the uh, edge of the depletion region, and you can see that it is a function of the depletion width now. So it is not a geometric only, and we can say that the accumulation and depletion, when we change the depletion width, the capacitance of the depletion changes, and it is inversely proportional to the capacitance, as you can see. So the total capacitance, if you just consider, is nothing but the series combination of the Cox and the C depletion. Cox and C depletion will give us the total capacitance, as we know, is in the series case is C dip times C ox divided by C depletion plus C ox. And when we increase the VG further, the depletion goes on increasing and hence C depletion decreases, which essentially means the total capacitance, this C, also decreases. So C decreases when we increase the VG, which will increase the depletion width. Okay, so this is also an important connection to remember. And the C, total C goes to a minimum value called as C min when the depletion width is maximum. So C is C min at W is equal to W max. Okay, so that we have covered. Also, when we go to the third region, the inversion region, so there is a we need to consider the applied signal frequency. So as we know that in both the accumulation and depletion, the majority carrier response is needed, and the majority carrier response is quite fast in, let's say, in few picoseconds. So it is very fast compared to the applied frequency. But when we go to the inversion region, and we know that the inversion region uh, is because of the formation of electron hole pairs, EH pair formation, and it requires a finite amount of time, and hence if the frequency of the applied frequency is very fast, I mean the timing is very fast than the hole pair electron hole pair generation time. So we can see that for the high frequency region, the EH pair formation does not happen and the balancing charge appears at the edge, and it is again the function of the depletion width. So it continues with C min for the inversion region. On the other hand, if we applied a low frequency, the electron hole pair generation takes place and the balancing charge in this case is similar to the accumulation region, and it tries to be ideal with the accumulation region, and you can see that the LFCV, that is low frequency CV characteristics, are quite opposite of our high frequency characteristics. Okay, so if we move to the next slide, I think this is about the MOSCAP CV characteristics. So the characteristics, again, I have just summarized few results here. So the C max, that is the maximum capacitance, is actually the oxide capacitance only, which is a geometric capacitance, and the C min, which is the function of both the oxide capacitance and the depletion capacitance, is shown here. Also the capacitance per unit area when the low frequency and the high frequency we are separating things. So you can see the capacitance for the low frequency range and for the high frequency range, how the biasing condition for the NMOS capacitor is for different regimes in the CV characteristics. Also the threshold voltage, as you can see in this figure. So this is the voltage at which the inversion actually takes place. Inversion region begins to happen, and that is given as a function of the flat band voltage, the phi ms, which is the difference of the phi m and phi s, and other parameters like phi s, phi f. So phi f is nothing but the, just a moment, okay. So phi f, which can be calculated using the carrier density and the intrinsic charge concentration. So phi s is 2 pi f for the inversion case. Going to the third slide, which is for continuing the recap. Again, I have summarized few of the results here. The flat band condition, the flat band voltage is given by the phi ms, which is the difference of the work function of metal and semiconductor, minus q prime ss by C ox, where q prime is basically where q prime is actually the qi is the trapped charge near the interface. So we also saw in the previous case, previous week, in fact, that we considered only the ideal MOS capacitance, but in the real world there are different non-idealities that take place, one of them being the trapped charges near the interface, and then next point is the maximum depletion charge, which is given by this particular relation, which is function of the charge carrier concentration and the xd max. Again, same goes to the electric field. This is the equilibrium condition that we have used several times. This is the depletion layer width and the maximum width, which happens at phi s. When phi s becomes to phi f, we get into the inversion layer, and xd max is given by this equation. One more important parameter is the effective oxide thickness. So we have seen that the capacitance is by silicon oxide, this oxide, by the thickness of the oxide. So when we want to increase the capacitance, what we do is we decrease the thickness as much as we can. So we, in the technological terms, we say that we are using 6 nanometer technology, 10 nanometer technology. But it basically refers to this thickness, the thickness of the oxide material, or the uh, what do you call, the insulator that is used in the MOS capacitor. However, there is a limit, and that is because of the quantum tunneling that happens when the Tox becomes fairly small, and that leakage is not ideal for our MOSCAP functioning. So this Tox brings us some limitation to improve the capacitance. So what we can do is we can look at the numerator, which is the epsilon for the oxide, and here we can try to increase this particular function, this particular numerator, but this is fixed for a particular oxide. So people have used different oxide material, some call it as HFO2, which has higher dielectric constant than your silicon dioxide. So which basically brings our purpose into reality, that the capacitance can not only be increased by decreasing the thickness, but also by increasing the epsilon, that is dielectric constant for the uh, dielectric constant of our oxide. Okay, so here one important parameter that we can define is the effective oxide thickness, or the equivalent oxide thickness. So equivalently, the oxide thickness, let's say TeOT, is the epsilon of oxide and the regular oxide, and epsilon of the high K dielectric that we have used, times the thickness of the high K. So effectively we have decreased the thickness just by increasing the, just by using a material as oxide which has higher dielectric constant. So effectively we can say that the thickness has decreased, and this has decreased by a value of this particular ratio. Okay, so let me go to the final slide for the summary. Here we also saw that the MOS capacitor's CV characteristics are dependent upon different parameters, such as the carrier density, the charge carrier density, uh, then the thickness of the oxide layer, and also the temperature. So you can see this dependence being shown here. So we can see that the threshold voltage where the inversion regime starts to happen, admit. Okay. So the inversion region where Vt, where the inversion region begins to happen, is actually have increased when Na, which is the carrier density, is increased, that we have discussed in the lectures also. Going to the next parameter, that is the thickness of the oxide, we can say that in this case we are talking of n type substrate, that is PMOS. So for PMOS we can say that the thickness is also does the same as the charge carrier concentration does. So the magnitude wise, the value of the threshold voltage also increases when Tox we have increased. So these plots sir have done it in that utility. You can see for the third parameter, which is the temperature dependence, and again we see that for the accumulation and the depletion regimes, there is no significant difference here for different temperatures. However, when we go to the inversion region again, so the more temperature gives us more electron hole pair generation in the depletion region, that enhances the electron hole pair generation. And so what happens is our capacitor, the MOS capacitor, tries to behave as the like a standard capacitor. So temperature increase, here no significance. So the temperature increase gives us more ideal or the standard capacitor like behavior, where the capacitance is purely geometric in the standard capacitor. Okay, so I think I think this is about the summary, and we can start with the problems now. Okay, so the first problem is quite simple and conceptual. I want you guys to just answer here. So the question is, the surface potential in NMOS capacitor at the threshold voltage is. So can anyone just turn on your mic and just give your thoughts on this? We know that the threshold voltage is at when Vt is at 2 times phi f. So now tell, what is the value of phi f? How you determine value of phi f based on the concentration and the intrinsic charge concentration, etc. I think this should be fairly straightforward, guys. Anyone?
Option.
Sorry?
Second option B.
Yeah. Yeah, so I was wondering like why you guys are taking such a long time. Okay, so the options B is indeed the correct option because it happens at twice the Fermi function, Fermi potential indeed. Going to the second problem, this is a calculation based. I'll just read out the problem for you. Consider a NMOS capacitor where the gate is made of N plus polysilicon and which has the doping concentration given, and also the oxide thickness is given as 50 nanometer. The flat band voltage is also given, and we are asked to find out the threshold voltage based on different other parameters. Okay, so if you go to the recap slide also, we know that our threshold voltage as a function of flat band voltage and the charge depletion charge, we can write as P flat band minus the depletion charge over the oxide capacitance plus phi s. For the Vt it is 2 times phi f. Okay, so let us find out each parameter first and we can just substitute it in this particular equation. So first and foremost, let us find out phi f, which is nothing but kt ln Na over Ni. Na is the charge carrier concentration, doping, and Ni is the intrinsic. So if you just maybe someone want to just turn off the mic. Okay, here. Okay, so if you just substitute it here, we'll get the value of phi f 10 to the power 16, where Ni is 1.5 times 10 to the power 10. So we'll get the value of phi f as 0.347 volt. Okay, so we have got phi f now. Let us try to find out the depletion charge. Maybe Bhuvanesh, is your mic on? Can you just turn it off? Yeah. Okay. So if you go to the depletion charge, we can just find it out by this particular relation, which is a function of the charge concentration and the depletion width. So also the depletion width we can determine by this particular relation. So here we are using multiple relations, substituting in other equation and then finding out particular parameter, which again we are using in the final relation. So you just have to remember or correlate all these relations. Okay, so if I just put the value of x depletion in this particular relation, we'll get the value of depletion charge as, just is a mere substitution. Okay, I'm writing just a final value here. Okay, so this is about the QD, and third is the Cox. So Cox also we don't know. So let us find out Cox. Well, Cox is fairly straightforward, which is nothing but the epsilon ox by the Tox. So epsilon ox is 3.9 times 8.85 into 10 to the power minus 14 farad per centimeter divided by the thickness, that is 50 times 10 to the power minus 7 centimeter. Okay, we are using the same units, which will give us the value of Cox that we can put. So we'll get all these values and finally put in our main equation, that is Vt. So let me just write it for you. Vt is V flat band, that is -1, -1. So minus the QD is negative, so minus minus becomes positive, and we'll get 4 times epsilon silicon QNA by F by the value of Cox, whatever it is, plus the 2 times phi F, 2 times this value, 2 times 0.347. And okay, so if you just calculate it, I'm not going to do it here, I'll just write the final value. Just substituting all these parameters, you will get the value of Vt as 0.394 volt, which is this answer. Okay, so this was quite a bit calculation. Let us go to some conceptual question then. Question number 3. Okay, so the typical high frequency MOS capacitance is less than the low frequency capacitance in which regions of the operation? Okay, again a fairly straightforward question. Can I have answer from you guys? Excuse me. The answer is more simpler than you think, so just attempt it. Hello, anyone?
Accumulation and depletion.
How accumulation you think? If you can just go to the characteristics here.
If you have a look at the CV characteristics.
Yeah, so that's what I'm saying. In the CV characteristics, accumulation is this region. So it is same for low frequency as well as for high frequency. The only region where it matters mostly is the inversion region, where actually the electron hole pair generation is an important factor, and so the answer is only inversion and not the accumulation. Did you get it?
Could you repeat it?
Yeah, sure. As you can see in the figure on itself, so this is for the depletion as well as accumulation, and all the characteristics are shown here. So this particular picture, in it we can see that in the accumulation region and also in the depletion region, the high frequency and low frequency does not affect, because high frequency affects only inversion region, where the electron hole pair generation is a factor which is dependent upon time, like how fast the input signal is varying. So only in the inversion region the timing, or say the frequency, matters, so to say, and not in the accumulation and the depletion regions. Hence, you can see that in the inversion region, the high frequency characteristics is lower than the low frequency characteristics and not in the other regions. So that's what is asked. Okay, yeah. Okay, so after this question, let us go to question number 4. Okay, so this is a question, again a quite simple question based on the CV characteristics only. So this is the high frequency CV characteristics shown for the ideal MOS capacitor as shown in the figure. So it is based for the question number 4 and 5. Again, straightforward, can you tell me which type of MOS it is? Is it a PMOS or a NMOS? Guys, please answer.
PMOS.
Yes. Okay, so just explain it further. Why do you think it is a PMOS?
Okay, so for the negative values of voltage, we see the
Dep-
capacitance is at its lowest point,
yeah, yeah,
and it should only happen at that region because the depletion width is maximum at that point. As it's happening for negative values, that should be a PMOS.
exactly, exactly. Very good. Okay, so this is for PMOS, which nothing but the N type substrate, and we also know that when we apply the positive gate voltage, the accumulation of the negative charges, which are the majority carriers in the N substrate, gets accumulated. So this is indeed the accumulation region, and this is accumulation region because it was N substrate, which corresponds to the PMOS. So indeed the PMOS is correct answer. Akshay has explained it nicely. Okay, so the fifth question, which is also based on this particular figure, is as follows. The question is, for different biasing conditions are mentioned here. Identify the corresponding points mentioned on the MOS CV plot. So we just need to write down different numbers based on different regions. Okay, I think I'll just explain it again here. As I have told just a minute ago, that this is the accumulation region. When we apply the positive potential, the majority carriers get accumulated. So this is the accumulation region. So the fifth point is indeed the accumulation point. Fourth point is the flat band voltage. This is the flat band condition happening. And when we apply the negative Vg, that is Vg in the negative direction, the depletion of the majority charge carriers occurs as the majority carriers, which are electrons, are pushed away from the uh, interface, and we can see the capacitance in the depletion mode being decreased. So this is indeed the depletion region, and as we know that at a particular voltage called as V threshold, for which phi s is twice phi f, we get beyond this point the inversion regime, where the N substrate effectively behaves as a P substrate near the interface. So the fifth point is, let us do it here. Okay, so the flat band voltage is at 4, inversion happens at 0.1, flat band is at 4, inversion region is at 1, inversion happens at threshold voltage, which is at 2, and the accumulation is in the fifth point, accumulation, and the last is depletion. So depletion is in the third point basically. Am I clear here, or do you have any doubt in this question number 4, 5? If not, I think I'll move to the question number 6 then. Okay, again the question number 6 is also a conceptual question, but easier one. So the question is, the threshold voltage Vt, of a MOS capacitor decreases with increasing or decreasing the gate oxide thickness and decreases with increase or decrease in the substrate doping concentration. Okay, so we saw that the Vt is given by, okay, someone wants to enter. Okay, so as I said, the Vt is given by the Qd, which is nothing but the depletion charge times the oxide, over the oxide capacitance plus twice phi f. And we know that when in our case the Vt is decreasing, so when Vt decreases, that means the Cox is increased. So Vt is decreasing. It happens when Cox increases, and we know that Cox and Tox are inversely proportional. So Cox increases, that means Tox decreases. So Vt decreases when Tox decreases. So decreases is one option. So decrease is one thing. Now about the substrate doping concentration. So this particular thing matters in this particular uh, parameter here, phi f, as we know that the phi f value is given by kt ln of n a or n, whatever maybe the type of the substrate, divided by the concentration. So when we increase this particular value, the value of phi f is also going to be increased. So this particular parameter increases, and we see that when Vt is decreased, that means this particular parameter is decreasing. So Vt decreases when phi f decreases. Phi f decreases when the substrate doping concentration also decreases. So in this case also the decreasing is the correct option. So decreasing, we have, I think, option 1 2 3, fourth option is the correct option. So I can just read it again. The threshold voltage of an MOS capacitor decreases with a decrease in the gate oxide thickness Tox, and it also decreases with a decrease in the substrate doping concentration. Okay, so that's about the question number 6. So let us move to question number 7. So this is a common data question for question number 7 and 8. I have taken it from GATE EC GATE 2007. The question is, consider a MOS capacitor of area 4 times 10 to the power minus 4 centimeter squared, and the dielectric constant of the silicon is given as 1 times 10 to the power minus 12 farad per centimeter, and the dielectric constant of the oxide, that is silicon dioxide, is given by this particular number. Okay, so let's go to the first question based on this data. The question is, the gate oxide thickness in the MOS capacitor is. So they have asked us to find out the thickness of the MOS capacitor, gate oxide thickness basically. So based on the figure itself, we can see that the capacitance is given, and it is given in the picofarad. So we know that the capacitance for the oxide case is the oxide dielectric constant divided by the thickness of the oxide. Now it is given in the picofarad and not in the picofarad per area, so we need to multiply it by the area of the capacitor. So we'll get, this is the correct relation. So using this relation we can just find out the thickness. So Tox is nothing but epsilon ox by Cox times the area. Okay, so what is the value of epsilon ox, which is the silicon dioxide? That is 3.5 times 10 to the power minus 13 divided by the capacitance. Capacitance is given. So C, we know that at the flat band voltage, this is the oxide capacitance. We know that C by Cox is equal to 1 in this region. So this is the oxide capacitance indeed. So it is 7 picofarad. So which is 7 times 10 to the power minus 12 farad, and area is also given, that is 4 times 10 to the power minus 4 centimeter squared. So if you just calculate it, you will get the value of the oxide thickness as T ox, nothing but 197 nanometer. So the closest answer in our options is, I think, 200. Okay, so the gate oxide thickness in the MOS capacitor is 200 nanometer. Let us go to question number 8, which is again based on the same data. The maximum depletion layer width is in micrometer. So what they have asked is the maximum depletion width. So as we have discussed, that the maximum depletion layer width happens when we are in the when the capacitance is minimum. So C min when the W dip is max. And if you go to our figure, you can see that the minimum C is, that is C min, is 1 picofarad. So we need to find out the maximum depletion width. Okay, so one relation we know, that the C min, which is the function of the depletion capacitance, that is C dep, plus the oxide capacitance, that is 1 over C ox. So if you just solve for C depletion, we'll get C min times C ox divided by C ox minus C min. Okay, so C min we know that is 1 picofarad. C ox, which is the maximum capacitance indeed, is 7 picofarad. So it is 1 times 7, or C ox is 7 minus 1. So it is 7 by 6 farad. Okay, picofarad indeed. We are talking of pico. We have substituted pico units here. So C dep we have got. So if we just define C dep here, it's as a function of the thickness. Maximum depletion width times area again, and epsilon silicon is the substrate dielectric constant. So we know the C depletion, we know epsilon silicon, also the area. So we can find out C depletion, which is maximum. So if you solve it for C dep max, you will get epsilon silicon, which is 11.9 times 8.85 times 10 to the power minus 14 times the area, which is 4 times 10 to the power minus 4 centimeter squared, divided by the C dip value, and which is nothing but 7 by 6 picofarad, that is 10 to the power minus 12 farad. So if you just calculate this, we'll get the value of maximum depletion layer width as around 0.00036 centimeter. So in micrometer they have asked us, so it is nothing but 3.6 micron. So the close relation, the closer answer we can pick here as 3.4. So the maximum depletion layer width is 3.4 micrometers. Okay, so let us go to our last problem, and this is also I have taken from GATE exam. It is for EC GATE 2020. The question is as follows: the band diagram of a p-type semiconductor with a band gap of 1 electron volt is shown. So this is the band diagram of a p-type semiconductor is shown. The band gap is 1 electron volt. So this references 1 electron volt. Using this semiconductor, a MOS capacitor having the threshold voltage of minus 0.16 volt, the capacitance of 100 nanofarad per centimeter square, and a metal work function of 3.87 electron volt is fabricated. Okay, there is no charge within the oxide, so the oxide charges are 0, non-ideality is not present as far as the oxide charges are concerned. If the voltage across the capacitor is V threshold, what is the magnitude of the depletion charge per unit area? So the depletion charge per unit area they have asked. So if you just V threshold they have mentioned here, so if you just go to our summary slide and substitute the relation of V threshold with different parameters that they have given as input, you will get this relation, that is phi ms. V threshold is phi ms minus q ox over c ox minus q depletion, that is depletion charge over c ox, plus 2 times phi f. Okay, so they have said that there is no charge within the oxide, so q ox is 0, so this particular term is cancelled. Phi m and phi ms they have given, so phi m they have given, so phi ms we can find out. We know that phi ms is nothing but phi m minus phi s. So phi m they have given, that is metal work function of 3.87 electron volt. We need to determine phi s. So we know that the value of phi s is nothing but this difference. So from the vacuum level till the Fermi level. So it is, if you just substitute phi m first, that is 3.87 minus phi s is indeed this value, that is 4 electron volt, plus this, that is half EV, that is half of the band gap, plus this. So we know that it is 0.5, this total is 0.5, so 0.5 minus 0.2, this thing is 0.3 plus 0.3. So if we just calculate value of phi ms, we will get phi ms as nothing but minus 0.93 electron volt. Okay, we have got phi ms now, and phi f is also we can calculate. Phi f is okay, they have, okay, so phi f also we can calculate again by using the same thing, same relation as we have used earlier. So if we just substitute all these parameters, now let us substitute it. Vt of minus 0.16 volt, phi ms of minus 0.93 minus qd over c ox, plus if you calculate the 2 phi f, we will get phi f value of 0.3 electron volt. It is nothing but 0.610, the multiplication of 2. Okay, if you rearrange for the depletion charge, you will get it as simplified as qd over c ox as nothing but 0.17. We know that the substrate is p type in our case, that means the qd is negative, the depletion charge is negative, but we are asked to find out the magnitude only. So magnitude of qd is nothing but 0.17 times the oxide capacitance, and oxide capacitance they have given as 100 nanofarad per centimeter squared. So 100 nanofarad, that means 10 to the power minus 9 farad per centimeter squared, which finally gives us 17 nanocoulomb per centimeter squared. So the magnitude of depletion charge is indeed 17 nanocoulomb per centimeter squared. Okay, so I think we are done, but I think we are still left with 5 minutes, so I'll go with the final bonus question. Very simple question actually. So the question is, calculate the flat band voltage for a MOS capacitor with a p-type semiconductor substrate. The data given is consider a MOS capacitor with a p-type silicon substrate doped with the value of Na given as 10 to the power 16 per centimeter cube, a silicon dioxide insulated of thickness 20 nanometer, that is 200 angstrom, and N plus polysilicon gate is they have used, and the Q prime SS value is also they have mentioned here per centimeter square, charges per centimeter square. So 5 ms value is we can get from one parameter they have left to give as 5 ms from the polysilicon uh, graph. We can get the value of 5 ms as roughly 1.1 electron volt. This is also a given parameter for this particular configuration. Now we know that the flat band voltage relation is 5 ms minus q prime ss over Cox. So let us find out Cox first. Cox is nothing but epsilon ox by Tox. So epsilon ox in our case is 3.9 times 8.85 times 10 to the power minus 14 divided by the thickness as 200 nanometer, that is 200 angstrom, sorry, that is 200 times 10 to the power minus 8 centimeter. So we'll get it as 1.72 times 10 to the power minus 7 farad per centimeter square. Cox we have got. Now let us find out Q prime SS, that is equivalent oxide charge density. Q prime SS. The Q prime SS is they have given electronic charge per centimeter squared. So we can get the equivalent oxide charge density as 5 times 10 to the power 10 times the electronic charge, that is 1.6 times 10 to the power minus 19 coulomb. So we'll get the equivalent oxide charge density as 8 times 10 to the power minus 9 coulomb per centimeter square. Okay, so we have Cox, we have Q prime SS, we have 5 ms. So let us substitute here and we'll get the value of PFB as simply minus 1.15 volt. Okay, so one thing to note here is that the applied gate voltage required to achieve the flat band condition for this p-type substrate is negative, and if the amount of fixed oxide charges are increased, this is the non-ideal condition, the flat band voltage becomes even more negative. So it is function of the oxide charges and it becomes more negative in that case. So I think I am done with my questions. Do you guys have any question to ask?
So how did we get 5 ms in the last question?
5 ms. Okay, so 5 ms is actually a given in the question itself. So there used to be one particular graph sir have like shown in the regular lectures for polysilicon samples. So from that graph they have given the value of 5 ms also. So I don't remember the graph exactly. For polysilicon sample, the values of 5 ms for different samples it is shown. From that graph they have given this value as input.
Okay, okay.
Okay. Okay, so as I said,
I have another
yeah,
query.
sure, no problem. Go ahead.
Actually, there was supposed to be a live interactive session with the professor, right?
Yeah,
Did
so
it
that
take place
happened
already?
yesterday only, right?
Oh,
Didn't you join that?
actually, sir, I filled out the form. Actually, there was kind of misinformation, sir, because
I
in
see.
the Google form that was sent out to fill the questions,
I see.
the session and the time was mentioned as 16/9/2022, which is today, and the time as 4 p.m.
Oh, I see.
That's
Okay, so maybe NPTEL people have done that particular mistake. So I'll again just report it to them. But anyway, you can go
okay.
to the YouTube and as I mentioned you can find out the recorded live session that
Okay.
has been uploaded already. And the professor is going to do the one more session in the next week or the week after that.
Okay.
Okay, so this brings me to my last slide. Thank you, slide. Thank you so much again, everyone, for joining for this live session, and I hope to see you in the next live session. A short change in the next live session is that the next live session will happen on Saturday 24th September instead of Friday 23rd September, and this change is only for the next week. And again, as I told you earlier also, that you can go on to the NPTEL course site. On the discussion forum you can ask questions, professor, regular TAs, me, or among yourself also you can have a nice discussion. Also you can find out these recordings on my YouTube channel. If you could not join due to some reason, or you want to check something again, you are free to go to those recordings and check it out. So thanks again, and I hope to see you all in the next live session. Till then, have a nice weekend, and bye bye.